I'm going to put in pi over 2 here, and negative pi over 2 there, and 1. Actually, you know what? Let me do these in different colors, and that will really make it stand out. Let's do in pink, because this really sticks out. Pi over 2, negative pi over 2, 1, and negative 1, and then in purple, let's do arcsine. So arcsine is going to be in purple, and we know that it maps 1 to pi over 2, so this is going to be on the graph, and it maps negative 1 to negative pi over 2, so that's going to be on the graph. And because sine maps 0 to 0, arcsine is going to map 0 to 0, and then we get it looking like this. And this is supposed to be what it will look like. It's not very pretty, but what we get when we reflect the graph of sine on this restricted domain through the line y is equal to x, which I'll draw here. So it's supposed to be the mirror image there. If you want to see a nice picture of it, you can Desmos it. But that gets the point across. And so an important takeaway from this is the last thing we do before we move on to cos, is that the range of the arcsine function, we have to keep in mind that it's negative pi over 2 to pi over 2, because this is going to be important when we're solving like trig equations. Because if you plug arcsine of something into a calculator, you plug arcsine of some angle. Say I'm trying to solve arcsine of theta, or let's do a number. Let's say arcsine of some number k is equal to theta, because so sine takes in angles, right, and puts out numbers. The sine of an angle, and then we extend it to the whole real line, but the sine of an angle in a right triangle takes in an angle and spits out a ratio. So arcsine, the inverse, is going to take in a ratio and a number and spit out an angle. So say I have arcsine of k is equal to theta, and they say, okay, I get this is my theta here. This is what comes out of the arcsine function. Well, I know that the range of the arcsine function is negative pi over 2 to pi over 2. On the unit circle, that is this. That is the first quadrant and the fourth quadrant. So if I get this theta coming out of the arcsine function, well, this has coordinates cosine of theta, sine of theta. Now, of course, this isn't the only solution. Say I wanted all the solutions in 0 to 2 pi. Well, I also have, if I flip this across the y-axis and make a related acute angle of theta here, well, this is going to have coordinates negative cosine of theta, sine of theta. So the y-coordinates, the sine values, are going to be the same. So, and this is, of course, the angle that I get if I go all the way around by pi, and then subtract theta off from it. So if theta is in this first quadrant is a solution, then so is pi minus theta. Similarly, if I were to, and let me do it maybe in this green, if I were to get an angle, phi in the fourth quadrant, well, I know that there is also this angle. If I make a related acute angle of phi there, so keep in mind this will be a negative angle in the fourth quadrant, right? This will be a negative phi. So I'm kind of saying here. So say it gave me the solution. Whoa, negative phi came out. Negative, pi over 3 or something like that came out. Well, I'm going to put that makes this related acute angle in the neon green of pi over 3 or whatever it is with the x-axis. If I put the same angle there as the related acute angle in the third quadrant, the cosine values of that the sine values at that point rather, the cosine values are going to be different. This is going to be cosine of phi and sine of phi, and this one is going to be, negative cosine of phi and sine of phi. Because the y coordinates of these points, the cosine values are the same, just like the y coordinates of these points are the same. Well, so again, if I wanted the solution in 0 to 2 pi, I have to think, okay, what is this going to be? Well, I got here. I mean, there's always different ways you can get there, but if I want this, so first of all, I should have said before, if I want my solution in 0 to 2 pi, this negative phi was not in 0 to 2 pi. So I would have to go around by 2 pi and then subtract phi from it. So if this was a negative angle, then I would subtract that angle that it is the negative of. So if it was like pi over 3, if the solution that I got was negative pi over 3, I would do 2 pi minus pi over 3. But that would only be one of them. I would also want this one here, and this is given if it's in 0 to 2 pi, I would get pi plus this angle phi. So pi plus pi over 3 if it was negative pi over 3 that came out. So a great exercise, and I think we should leave this as an exercise, is to think, so suppose the same way, and I encourage everyone to actually draw this out and sort of reason your way through it the way that I've done here. What if instead of my solution being in 0 to 2 pi, I wanted it to be in, say, negative pi to pi, like that. So I can go around, let me do it maybe in blue, I can go around like that by pi, or I can go backwards by pi. Instead of the 0 to 2 pi, that was going all the way around the circle, and that gives me all of the points, and of course I leave out one of the endpoints so that I don't get it twice. The interval negative pi to pi is saying you can go forward by pi or back by pi, and that will give you all of the points as well exactly once. If you leave out one of the endpoints, doesn't really matter which. Think about how you could find if you got the arc sine of some number giving you a theta or a phi or a negative phi somewhere in between negative pi over 2 to pi over 2, how would you find the corresponding angles, the other solutions, if you were asked to do those on the interval negative pi to pi? And one step further, how would you find all the solutions? How would you find every single solution if you got the output of the arcsine function? How can I get every solution out of that? So that's a great thing to think about.